Hello students, after the interpretation of the gas chromatogram, now let us see that how this gas chromatogram actually help us in getting the quantitative idea of various components present in the vaporized sample. So let us begin our journey with regard to quantitative analysis in gas chromatography. So before dwelling into the main course, let us first understand the principle of quantitation. That what is the principle on which we can ascertain the presence of different quantities of different components of a particular vaporized sample which we have run by using gas chromatograph. So let us start with. We know that the peak area, the peak area, the peak area is directly proportional to the amount of substance injected. So here the important thing is that there is a close relationship between the sample which is to be analyzed with regard to the peak area of its peak area. Now the peak height is less reliable as compared to the area. So area, for example, this area, for example, if we have a chromatogram like this, okay, this is the detector response here, this is the detector response, okay, and this is the retention time, this is the retention time. Then this distance, if you call this distance as h, height of the peak, and this is the half width of the peak, then the area under the peak, area under the peak, area under the peak may be given as this area. We are talking about this area. So this area is given by h into the half width of this, that is W of 2. If this distance is half, then half of the peak width. So this is how actually we calculate the area, and this area is sensitive with regard to band broadening. And we have already discussed that if prolonged fronting is occurring, then what is the root cause of that fronting, and if we are getting prolonged tailing, then what are the different causes of that actually tailing. So detectors must actually have, an ideal detector must have linear dynamic range. That is, for a large quantity, the detector response should be proportional to the change in the concentration. That is what actually I mean to say, that if you change the concentration or if you change the quantity of the analyte which you are analyzing by using the GC, then the detector response will change. And for an ideal detector, that range should be as big as possible. For example, we have given a range for that flame ionization detector is 10 to the power 7. That is such a huge range. That is, your detector is sensitive to small changes with regard to the change in concentration or with regard to change in quantity with respect to the detector response. So for an ideal detector, this range must be as big as possible, and in this case FID is the best suited detector with regard to the linear dynamic range and also with regard to sensitivity of measurement. We have seen that it is actually somewhere 10 to the power minus 15 gram, the sensitivity. So FID is very good in this sense, but again there is a disadvantage of FID, that it does not work very good for inorganic compound. Okay, so let's start the calibration. So we have a number of strategies. Now the most important strategy is the calibration plot, by doing the calibration plot. Now calibration plot is actually a plot where we plot the area and of the analyte on the y-axis, and on the x-axis we plot actually the concentration of the analyte. So let us draw a calibration plot. So on the x-axis we have the concentration of analyte, and here we have area under the peak of analyte. So we get a calibration plot like this. And the importance of plotting this calibration plot is that now you can find the concentration of your unknown analyte present in your sample. So that is the beauty of this, that you can actually get the concentration of the unknown sample. Similarly, this calibration plot is very simple and it is also very sensitive with regard to the injection issues. For example, if you injected too much volume of your sample into the column, then it will show, it can be analyzed from at this place, because the moment you actually increase the capacity of your column, you will get some errors in terms of baseline. Similarly, internal standard. Actually, internal standard is very important, and internal standard is that compound which is used throughout the run, throughout the experiment, so that you can minimize, by using the internal standard, you can minimize the simple detector responses, issues of detector responses. For example, if you change the sensitivity, it will also adjust the change in a little bit of sensitivity. So this internal standard actually balances all the small issues occurring during the run. So it is always preferred to use these internal standards. Similarly, you have to, in certain cases you have to add certain compounds so that you can get a good precise result. Okay, precise as well as accurate result. There is a distinction between precise and accurate. Precise means that is your reading or your value should be as close to the accurate value as possible. Now, the response factor, actually it's a ratio. Response factor, it's actually ratio of the detector sensitivity of analyte versus the detector sensitivity of internal standard. Okay, so this is it. Now this internal standard is actually represented by IS. This is for internal standard. This A is area under the peak of the analyte upon concentration of analyte. Similarly, area under the peak of internal standard upon the concentration of internal standard. This RF value actually is very important. At higher actually RF value means that your detector is more sensitive towards your analyte rather than the internal standard. So a high RF value means detector is more sensitive. Towards analyte. So this response factor also actually corrects the detector responses also. For example, if you are changing your detector, then this difference of the two detectors can be minimized by this response factor. Okay, so let us examine a numerical to get a clear picture. For example, if the area of under the peak of an analyte is 3500 and area under the peak of internal standard is 2500, similarly the concentration of internal standard is this and the response factor is given to be 1.1, then you can put all these values in this equation and you can get the concentration of your analyte. So this is how this response factor actually helps in getting a good quantitative data from the GC chromatogram. So calibration curve, again it is very important. For example, calibration plot may be simply defined that on the y-axis you have plotted area under the peak of an analyte, while on the x-axis you have the concentration. And here actually m, which is slope, gives you the detector signal. And this actually C is the background response. It is the background response of your detector. So there are two things actually which comes into here, because this is a linear regression curve. This curve is actually used for the straight line curve. This is also called as a straight line curve. So this calibration curve gives you an idea to ascertain the concentration of unknown analytes. Now let us actually explore another important quantity, that is the LOD, which is called as limit of detector. Another thing is LOQ, that is, it is also called as limit of quantification, limit of detector, or you can say limit of detection. Now there are two quantities, that is the limit of detection, that is LOD, and another is limit of quantification. Now limit of detection in simple words may be defined as that actually quantity which your detector can measure, but that quantity cannot be transformed into a signal, cannot be transformed into a peak. That is called the limit of detection, LOD. Similarly, the limit of quantification is that minimum quantity which can also be depicted via a peak. That is why you can see it is 3 sigma upon m and this is 10 sigma upon m. And we are going to use these equations in our next slides, where we are going to do some numericals. So quantitative accuracy and precision, as we have already discussed, that accuracy may be defined as the closeness to the true value. That is, if your experiment is precise, then you actually got very close to the real value. Similarly, precision is actually the repeatability, that each time you have to have the same reading coming. So you say that your experiment is precise. So in terms of precision, the relative standard deviation must always be less than 2%. This is relative standard deviation, that is always less than 2%. For example, where quality checks are required, then your system must be actually precise and it should give accurate reading, and that can be seen by the tailing factors. So for a good quantitative analysis, your fronting and your tailing should be minimized. That is, ideally speaking, your peak should be Gaussian and narrow, as narrow as possible. So what are the applications of quantitation? That why we are interested in quantitation. So initially, for drug assays where pharmaceutical quality checks are required, where high accuracy are needed. For example, if you are administering certain injection to a patient, then you must be very specific that the prescribed amount is going in is there in the injectable and it is going in the body or not. Similarly, with regard to beverages, you should be very sure that you have the specified quantities, otherwise it may cause sedation and other issues. Similarly, where residual solvent testing is required. So always you have to have a good quantitative and qualitative result. Similarly, in terms of pesticide residues, where actually you need a detection range of parts per billion. So you have to have very precise and accurate quantitation of your sample. Now what are the common problems and how we are going to solve it? We are going to see few problems and their solution, hand in hand solution. For example, if peak tailing is going on, that is, you are having an ideal peak, but it is going like this. peak tailing is going on. Then this peak tailing might be because of the blocking of the active site of the stationary phase. That is, you can say that your stationary phase is having a strong interaction with the analyte, and that is why it is blocking the active sites. And sometimes there may be some column contamination, and because of this column contamination you are getting this peak tailing. So how you are going to solve it? Solution is also given here. So you have to use deactivated liners. Similarly, you have to use certain guard columns. And if still the problem persists, then what you do, you just take new stationary phase. So for example, if you remember when we were talking about the detectors, then in certain detectors we have chosen the liners so that your sample can go straight into the column. So those liners sometimes cause issues. So you have to deactivate your liners. That is, you have to actually clear the backlog samples of the liners. Similarly, peak fronting, that is, now it's opposite to peak tailing. That is, here actually you have a long peak, and this is the peak fronting. And this peak fronting is actually caused by because of the column overloading. That your column is actually have a capacity of 2 microliter and you have loaded 4 microliter of sample. So this situation creates peak fronting. Similarly, you have injected large volume of your sample. So again, the solution is here that you have to use dilute samples. And again, if you are encountering this problem, then you can use the split injection technique. And in the split injection technique, there was a split ratio. We have already discussed this split ratio. It may be 1:10, it may be 1:20, and sometimes it may be 1:100. And as you actually goes on increasing this ratio, you are actually going, for example, for low concentration solution, you always go for a lesser ratio. For high concentration, you are going to have higher concentration. Similarly, if you have a ratio of 1:20, then it means that out of 20 parts, 1 part is going into the column for the separation, you can say. So if you have 1:10, then only 1 part out of 10 part is going into the column for separation. If you have 1:20 ratio, that means only 1 part out of 20 going into the column for separation. If you have 1:100, then only 1 part. So for high concentration, you use this. For high concentration, you use this. For high concentration. For low concentration, you use these type of ratio, low concentration. Similarly, if we have given a very small, very simple numerical. For example, if you have an injection, if you injected 5 microliters of your sample in a column, and the split ratio is 1:20, then only 1 part out of those 20 will be going to the column for the, you can say, separation. So 20 microliter, if you do 20 parts, then the 1 part will come out to be 0.25 microliter. Okay, that is, if you multiply this 25 into 20, then it comes out to be 5 microliter, which is here. Okay, so this is how actually you avoid fronting. So now you have the solution to avoid peak tailing, and now you have a solution to avoid peak fronting. So let us move again. Now if you have a split or double peaks, if you get a like this peak like this, so what is the solution? So this type of peak occurs because of the poor injection technique. Or you have, for example, your solution was a volatile, and instead of using on head column, you have to use the splitless injection. Then this type of situation may occur. Similarly, there may be solvent mismatch, or sometimes what happens, your sample degrades. It may be thermal degradation also. So in that cases, you actually got this type of peaks, double peak or split peak. And what is the solution of it? Solution is you have to use fast injection ports, splitless. Similarly, you have to make sure about the polarity. that your solvent actually match the polarity of the stationary phase. Similarly, if still the problem persists, then you can use a fresh standards. Okay. So this is how you actually solve the problem of double peaks or splitted peaks. Similarly, retention time drift, it actually occurs because of the long use of the column. That is, if you are keep using the column for months and for years without cleaning it, without doing the calibration, without using the standards time and again, then your column will give you faulty results, and this may be sometimes because of the aging, because of the stacking of the previous components of your samples. So these are the causes, and the solution is that you have to recondition your column. You have to calibrate your oven, that your that is, for example, if you are using an isothermal column, then sometimes what you have to do, you have to run your column, increase the temperature to a little more, for example 250 degree centigrade, then the analytes which you have actually analyzed, which have is already stacked in it, they can be vaporized. So you can calibrate oven, and you can always check for leakages, that whether your carrier gas is flowing freely and is maintaining the volume, maintaining the pressure or not. So you have to check for every minute detail, that is whether there is some pressure drop, that is whether the pressure is maintained throughout the column or not, and what is the status of your rotameter pressure gauges. So you have to check each and every detail. Similarly, baseline drift and noise. So this actually, why this occurs? This drift or this occurs because of the additional or the increasing of the ramp. That is, if you have increased the rate of change of temperature with regard to time, then you will get certain drifts, or because of the column bleed. Column bleed is that situation in which you increase the temperature of your oven in such a way that your stationary phase, which is packed in the column, it actually starts decomposing, and because of the decomposing of the stationary phase, the stationary phase also starts eluting with the eluent, with the sample. So that is called as the column bleed. So you have to check for the column bleed, that whether you are increasing the oven temperature too much, more than that the boiling point of the stationary phase. So you have to check for the column bleed. Similarly, noise, because this noise actually creates instability, and sometimes the noise occurs because of the detector instability. So what are the solutions? Solution is again here, you have to use very high purity gases, free from any impurity, whether it may be water, whether it may be certain other gases. Similarly, you have to check for the column bakeout, that whether your column is, your stationary phase is intact or not, whether the volume which you have loaded on the stationary phase is equal to the earlier amount or not, or whether the some of the you can say stationary phase is actually wiped out with time, that whether the thickness is maintained or not. And you have to ensure the detector maintenance throughout. Okay, so after certain time intervals you have to check that whether the flame is properly lighting up or not, whether if for example if you are using ECD, whether your radioactive source is still active or not. So you have to check all those small details. Similarly, there are ghost peaks. Ghost peaks may be defined as those peaks which are not because of the presence of any constituent, they come out of their own. So those peaks which do not correspond to any component of your sample, that peak are called as the ghost peaks. So what are the causes of these ghost peak? That is carryover, that for example you have done certain experiment, you have run your GC, and before cooling it properly you started your next run again. So there may be chances of some carryover of your previous sample along with the new one. There are chances of septum bleed. Sometimes septum also comes along with the carrier gas, and that causes the creation of new peaks that are also called as ghost peak. Similarly, memory effect, that previous components are also coming. So what you have to do, how you are going to avoid those ghost peaks? by using blank runs. So just run the carrier gas alone, 1 or 2 runs. Similarly, you have to replace the septum on a regular basis. Similarly, by back flushing the inlet, just you can say, which you have done, for example, just like the degassing. So you have to back flush the inlet. So these are the issues of ghost peak and these are the solutions of ghost peaks.